Okay, in this part, we're going to talk about functional groups. Functional group, functional groups, function. They take part in a reaction. This is the site of a molecule where the reaction takes place. It's an arrangement of group of atoms with distinct physical and chemical properties, and those groups of atoms will take part in a chemical reaction. That's the site where the chemical reactions happens. Now, before we look at a complex structures, I would like you to know that organic chemistry is the chemistry of hydrocarbon structures, and the hydrocarbon structures could be modified with extra elements other than carbon and hydrogen. Where you only have carbons and hydrogens in the structure, we call that molecule a hydrocarbon. Like these ones are hydrocarbons falling under the class alkanes. Alkanes because all you got in here are single bonds or sigma bonds alone. There's no pi bond. Okay, so alkanes. Now in chapter 3 you learn, in chapter 2 you'll cover much on alkanes. In chapter 3 you'll learn about alkenes. These are the guys, the molecules which have carbon-carbon double bond. And then you'll also learn about alkynes, I think part of chapter 3, which have triple bonds. So where there's no pi bond whatsoever in the structure, in the hydrocarbon structure, that will be called an alkane. Where there's a double bond, at least a double bond, is alkene. Where there's a triple bond is alkyne. This will be covered in chapter 2 and 3. Okay, so what are these functional groups that take part in a reaction? Obviously, this is an alkene. Alkenes can take part in addition reactions. Alkynes and arenes, they will take part in addition reactions. And arenes, which just means it's an aromatic alkene, arene. This one is special because of resonance stabilization. Okay, so a specific example of alkene is given as ethene, because there's 2 carbons in the structure, or ethine. Here there's a typo, it should be a hydrogen. Again, there should be 2 carbons and the triple bond, so we have the suffix "ine" falling under the class alkynes. Carbons and hydrogens are not the only elements that can make an organic molecule. You do also have options of adding oxygens or nitrogens or sulfur or halogens. Halogens are group 7 elements. Halogens belong in the main group 7 elements. These are halogens right there. So you could have extra elements other than carbons and hydrogens. But now here these 2 guys have oxygens only other than the CHs. So where you have an OH at the end, that's called an alcohol. For example, here you have 1 carbon in the rest of the structure. So it takes the meth prefix name. So it's methane because it would have been derived from the smallest organic hydrocarbon molecule called methane, but the suffix E is replaced by OL. Methane. That's a methane. You replace the E, you get methanol. This will be discussed in a later chapter. All I want you to know is that alcohols are characterized by presence of OH. So let me just use R to denote any carbon tail, and then you have OH. Those will be alcohols. For ether, basically you want an oxygen between 2 carbons, and these 2 carbons should not bear another oxygen on top of them, like a double bond O. We call it a carbonyl. So this will be the general structure of an ether. So generally you'll have ROR, where R and R prime are not the same chains, may or may not have the same count of carbons, but you do have carbons in there. I'm just using R to represent any carbon part of the structure. Okay, that's the other functional group. Now, I'll want to mention here that alcohols are more polar than ethers. Okay, even though both of them have oxygens. We'll discuss polarity later. Now, what if you have a CO double bond? So let's say you have a double bond there. So this is a carbonyl. I just corrected there the notes. That's a carbonyl. Okay, we call it a carbonyl, C double bond O. So where you have a carbonyl attached to a hydrogen on one side and a carbon on the other side, that's called an aldehyde. So generally this is the representation of an aldehyde. Okay, and then it's commonly confused with the ketone. For the ketone, you'll have a carbon and then the carbonyl, the C double bond O is called the carbonyl. And then you have another carbon. So you see, notice there's no hydrogen there. So that's a ketone. Specifically, this is an example of a ketone. It's acetone. That's the nail polish remover that you use to remove nail polish from your nails, fingernails. And then this is acetaldehyde. We'll name these ones in their own chapters coming up. So they are functional groups again because they react. They are attacked by what we call nucleophiles. These ones by themselves will be electrophiles. We'll discuss that in way later chapters. Okay, now what if you have a mixture of a single bond, single oxygen bond, and single double bond O bond? So what if you have a mixture of a carbonyl and a CO? So there are two possible ways. So if the carbonyl is bonded to an oxygen and there's a hydrogen here, at least a hydrogen, and here there's a carbon structure that goes blah blah blah, I would have called that R group. This would be the carboxyl group. It's a carboxylic acid. So specifically, one that has two carbons, the carboxylic acid, two carbons, is called ethanoic acid because eth stands for two carbons. It's called ethanoic acid. That's the UPAC name, the official name. Okay, but here you have a carbon to a carbonyl to an oxygen to a carbon. See, spot the difference. Here you have a carbon and a hydrogen. Here you have a carbon and a carbon. So this is the general representation of an ester functional group. They usually smell sweet, mostly found in fruits and perfumes. Anything that smells sweet will most likely have an ester in it, just like the sweet smell that you get from, or the aroma I should call it, that you get from a ripening banana. It's full of esters. Apart from oxygen, you might also have nitrogens in the structure. So the basic nitrogen containing molecule, of course, it's ammonia. Okay, this is just ammonia, and I'm gonna add some more information here. So the moment you add, remember the nitrogen has to be octet. That's how I knew that I need to put 2 more electrons because this was 6. The moment you add a carbon on one of these hydrogen, so let's say this R group contains a carbon in it directly bonded to nitrogen, then this will be called a primary amine because there's one carbon attached to the nitrogen. So for example, this is generally a primary amine. Is a type of amine substituent, or is a type of substituted amine. The moment we replace 2 hydrogens in the ammonia with 2 carbons, they may be the same or not. And I'm using R because R could be CH3, an ethyl group, a methyl group, a ring, carbon containing ring, and all that. So the moment we replace 2, this becomes a secondary amine. And then when all the hydrogens are replaced by carbons, for example, there's a carbon directly attached to the nitrogen. So I'm going to use R groups to generalize, R1, R2 and R. This will be tertiary amine. So I'm writing this extra information here so you relate whenever you see them in a question. So anyway, it's all those amines, all these are amines, only that they are substituted differently to get primary, secondary, and tertiary. I mean, not 1 degree, 2 degree, 3 degree. No, we are not measuring angles. We are saying it's primary, secondary, tertiary. So this is a primary. Why? Because all these carbon part here is an R group. So you only have one R group onto the nitrogen, so it's primary amine. Specifically, it's called methyl amine because that's the methyl part. And of course, it's an amine because there's a nitrogen part there. This is an imine where the nitrogen is doubly bonded to a carbon with a lone pair on it. It's called an imine. You have 2 carbons, so it's ethylamine. And then here the carbon triply bonded to a nitrogen is a nitro group, or nitrile group, sorry. Specifically, this should have been called ethonitrile, but the common name is acetonitrile. And then this is an amide. Amides will simply have this type of a structure, okay, where R could be a carbon containing group or a hydrogen. For this part only, I'm using R's. In this case, the R's could be either carbons or hydrogens. Here, in this case, the R should be carbon containing groups. So this is the general structure. So that's an amide, and amides are important to make peptide bonds in DNA, RNA, and proteins. Okay, so next you have sulfur containing groups. We've talked about oxygen containing groups. Oxygen, starting from here, we talked about oxygen containing groups, oxygen containing functional group. We talked about nitrogen containing functional group. Now it's the sulfur containing functional group. These are thiol, and these thiols are responsible for the fall smell in skunks. I don't know if that's the spell of a skunk or there's an A. You know what a skunk is, the animal that releases bad smell from their behind. So that's a thiol. They give thiols out, and there's one carbon, so this is called methane thiol. We'll talk about this when the chapter comes. And then if the sulfur is in between 2 carbons or between 2 R groups, it's called a thioether. Compare this is an ether because the sulfur is between 2 carbons. This is an ether. The oxygen is between 2 carbons. Only that here we are specific, saying that's dimethyl sulfide, but here we would have called it dimethyl ether. But both of them are types of ether. So these are sulfur ether, this is an oxygen ether. Okay. The last functional group is simple. You have halogens. Those are main group elements. Halogens bonded onto carbons give you a haloalkane, otherwise called alkyl halides. You will have to use alkyl halides a lot. I think chapter 7, 8. And then the isochlorides, you'll have a carbonyl directly bonded to a Cl. Remember, I told you this one here is an aldehyde. If you have such an end on a molecule, that's an aldehyde. So this will be called isohalide, but this one will be haloalkane or alkyl halide. Okay, now let's practice. This monstrous structure here is of a drug called Taxol. That's the brand name. Taxol is approved by FDA in treatment of certain cancers. So it's used in treating certain cancers, types of cancers, breast cancer and colon cancer and so many other cancers. It's extracted from a tree, I think it's called the yam tree. This is can you imagine this is a drug people take? Very, very, very ugly, but it works. So I would bring in exam 1 such a structure and ask you to name that functional group. What's that functional group? There's a carbon, or there's an R group, there's an R group, there's a hydrogen, or an R group if you want to say so. This is called an amide. If you're doubting where I found it, you see how it looks, carbonyl and nitrogen. That's how I knew that's an amide. Very simple. This OH to a carbon, that's an alcohol. And then here you have a carbon, carbonyl, oxygen, carbon. So generally here you have this type of a structure. This structure right here, if I would circle it that way, is an ester. That's an ester. Okay. That's an ester. And this one will also be an ester. Okay. This part right here is an alkene. And of course, this one happens to be an alcohol. This part right here is another ester. I should have circled to this point. That's another ester. Of course, this is another ester right here. That's another ester. What will this be? I see a carbon right there. I see a bond, an oxygen, and then another carbon right there. This is an ether. That's an ether. Okay. COC. We talked about ethers right here. COC. That's an ether. Sorry, something is biting me. Okay. Next, this one right here is an alcohol. I would circle them and ask you to identify the functional group. This one, because there's a carbon here and the carbon here and the carbonyl, this one will be a ketone, not an aldehyde. Those are the functional groups I can quickly identify in this drug called Taxol, used in treatment of cancer, anti-cancer. Alright, so that's it. Let's see. We need to know how to draw structures. These molecules, the way they're drawn, you can see they're just too busy. Usually, we don't want to show all these hydrogens. Or we don't want to show too many bonds. So one would say, I could condense this structure, okay, and say this first carbon right here is bonded to two CH3s. So why not put the CH3s in parentheses and put 2 there, and then this carbon will be the CH, and then you see you have 3 CH2s. So one would say I would put CH2s again and then put a subscript of 3 and then finish with the last CH3. Okay, so this would have been the condensed formula, but still it's too crowded. So instead of doing this, what we usually do is just to draw the bonds, and whenever and draw zigzag shape, and wherever the corner is, the angle is, that's where the carbon will be found. So for example, at the end you'll have carbons, which is this and this, and then this carbon right here happens to be this carbon, and then we go down to the CH2, up to the next CH2, down to the next CH2, and then up. You could start the other way by flipping this molecule, it doesn't matter. So notice that I have 1, 2, 3, 4, 5, 6 carbons, which means I should have 6 carbons in my what we call the line angle formula, line angle structure, which is what I would expect you to use. So 1, 2, 3, 4, 5, 6. I still have 6. So at each ends and beginnings of the chain, you have a carbon. So the one that's out there is called a substituent. We usually don't count it. you will name alkanes in chapter 2, and you'll see we always number only the longest chain in the structure. Now one will ask, where is the hydrogens? Where are they? Now I want you to remind you that carbon can take 4 bonds, right? Carbon can take 4 bonds. So I don't need to show the hydrogens yet. It could be bonded to hydrogens or oxygen or another thing. It doesn't have to be hydrogen. So I'm gonna clean this up so that I emphasize that carbon has a valency of 4, which means, and which is why carbon can bond to four other elements. So it could be like that, or the carbon could be doubly bonded with 2 single bonds, or the carbon could be singly bonded to one element on the left and triply bonded to another element on the right. It's still 4 bonds around it, or the carbon could be between 2 double bonds. These are the combinations on how carbon can be bonded. So now I counted the bonds here because that's gonna help you know how many hydrogens are implied. For example, in carbon number 1 we have 3 hydrogens. You see you only have 1 bond to this carbon number 1 because I told you carbons must be in the beginning of the line angle structure. So we only have 1 bond to that carbon. We are missing 3. Those 3 are going to the 3 hydrogens outwards. I don't want to draw them, but they are there. So for clarity reasons, we usually don't show hydrogens. So here, this carbon number 2 has 3 bonds around it, which means 1 bond is missing. It's actually there, it's just not drawn, bonded to the hydrogen. The hydrogen is there and it's actually there. We just don't show them. We don't show them for clarity. And the rule is whenever you have hydrogens bonded on carbons, don't show those hydrogens. You don't need to. In fact, even the carbons, we don't need to, because I know the beginning of each line is a carbon. The end of each line structures is a carbon. Where the hydrogens are bonded to oxygen, nitrogen, sulfur, etc., those hydrogens must be shown. For example, in amines, in alcohols, or thiols. Okay, so this one, following the same scheme, I would condense it to CH3, then I do CH2 because it's repeated twice, and then the bond to the carbon, but this carbon is bonded to 3 CH3, so I'll write CH3 and then 3 on the outside. But again, it's too busy, so what I'll do is just to draw like this. I know I have 1, 2, 3, 4, 5. Whichever way you number it, you end up with 5 carbons. So I should start here 1, 2, 3, 4, 5. The 4th carbon seems to be bonded to 2 CH3, so those ones will be drawn up there as a stick. Usually whenever you're drawing carbons shared on one carbon, you want to crisscross them. So there should be a peace sign up and a peace sign down. That's how I knew this is how I'll draw the groups here, like peace sign up, peace sign down, because remember, you want to keep the tetrahedral geometry, which is 109.5 degrees. That's why I did not draw it. I did not draw this part with the 2 CH3s pointing down, because that would be messed up. I want them up. You have to practice to draw them, because that's the language of organic chemistry, and that's how you're gonna excel in this class, by knowing how to draw these structures. So remember, I said the hydrogens bonded to any element other than carbon must be shown. So I'm trying to draw the condensed formula again. See, this is condensed, this is condensed, okay, and I'm gonna draw the condensed version of this. So I have 1, 2, 3, 4 CH2s, so I'll put CH2s and put 4 outside, and then I have a CH, and then the NH2 should not pop out, so I'll put it in parentheses because it's bonded to the CH. And then of course I cannot condense the alcohol as much other than just doing that. Okay, but again, this is too busy, so if I wanted to draw it well, what I'll do is I'll have to show the hydrogens to the nitrogen, and then I have to repeat these angles 4 times. 1, 2, 3, 4, representing the CH2s. And then there's a CH, which is bonded to an NH2. And then there's a carboxyl acid. I have to show the hydrogen on the oxygen, because we only imply hydrogens bonded on carbons, but not on other elements. Okay, so again, remember here, I'm not showing the 2 hydrogens. For example, in this carbon, it's gonna be this carbon. I'm not showing the 2 hydrogens. They're there. Each carbon must be bonded to 4 other things if it's neutral. So the hydrogens are there. I would have drawn them here like this. I would have drawn those hydrogen like that with the 2 bonds. So let me clean it up so that you can clearly see it. So I would have drawn them like that. And same thing here. Remember the 2 crisscrossing peace signs? You want the opposite V's, and this one would have been up here. But like I said, because the hydrogens are sitting on carbons, we don't show them for clarity. So we get rid of those. For the line angle formula, we get rid of those hydrogens, and we just leave the line angle, because we know each of the corners, each of the V's where the bonds are meeting is a carbon. So that's how I'll draw the line angle formula for this one. So this will be the line. So that's the condensed. This one is a condensed structure. This is the line angle formula or structure. Okay, so here the line angle formula would be this without okay, let me start with the condensed. So the condensed would be the condensed structure formula would be like this. The CH2 is repeated 1, 2, 3, 4, 5 times, and then I'll have to show the hydrogens on the nitrogen, because those are not implied. You only imply the ones that are on the carbons. But for the line angle formula, okay, for the line angle formula, I wouldn't show the hydrogens on the carbon, so I'll just repeat and show 5 corners, 1, 2, 3, 4, 5, and finish with NH2 again. So again, the line angle formula is what we prefer in this class or in organic chemistry. 1, 2, 3, 4, 5. The hydrogens are implied. They are there. Each carbon should have 4 bonds, so the hydrogens are there. Okay. So I've talked about condensed formula, and I really don't need to discuss much on this because I've done much of the examples here. I want to just to insist that even the condensed formula can be very tedious to do. Like you've seen, it's taken time for me to do all this. So we would want to use line diagrams or line structures. Those ones are the ones which are the best. Now let me do a correction here. We need a CH here, okay, bonded to this. So here the line formula will be like this. 1, 2, 3. Okay, so I have the 3 CH2s. I'm just circling them for purposes of teaching. And then this CH3 is that one. And then the 2 CH3s is that and that. There's 3 bonds here, so there's a hydrogen implied, which will be this that was missing because of typo. Same thing here, there's a typo. You will need a CH in between. So again, the line angle, the 2 metals will be outside, the CH will be right here, and then I have to repeat the CH3 3 times and then finish with the CH3. So that's the CH3. This part right here are the 3 CH3s, and then this carbon right here is definitely this carbon right here in the middle. The hydrogen is implied, is there, it's just not shown. And the CH3 too, the 2 CH3s are these ones at the end. And then same process applies here. I have 2 CH3s to a carbon, and that carbon is bonded to 3 metals. So these 3 CH3s are these 3 fingers out here. This carbon is this carbon in the middle, and then of course that's the CH2 right there, and that's the CH2 right there, and that's the CH3 right there. Get used to writing structural formula in form of line diagrams. So in summary, if you want to draw the line diagrams, of which is what I prefer, you want the carbons and hydrogen atoms not shown. The carbons will be the vertices, the hydrogens will be on the carbons, just not shown. Just remember to count 4 bonds around each carbon. Okay. We do that for emphasis or clarity. So all atoms other than carbon and hydrogens must be shown very well. For example, the nitrogens must be shown, oxygens must be shown, sulfur must be shown. So you don't imply them like we implied the carbons and the hydrogens. Okay. A carbon is always assumed to be at the end of each chain, like there and there. There's a carbon at the beginning and at the end. Okay. Multiple bonds are shown with multiple lines. For example, if you have a double bond and triple bond, that's what we'll do. There's gonna be a carbon here, there's a carbon there, there's a carbon here, there's a carbon here, there's a carbon here. Now it's your role, your job right now to fill the 4 bonds. If you are to show the hydrogens, there's gonna be 2 hydrogens there because each carbon must have 4 bonds. There's 1 hydrogen, there's 2 hydrogens here, and of course there's 1 hydrogen at the very end. So the very clear structure will look like this if you are to draw it without showing carbons and hydrogens. Okay, that will be the line diagram. So that is point number 4. Multiple bonds are shown in using multiple lines. The proper number of hydrogens atoms to provide 4 bonds, I insist again, each carbon must have 4 bonds to each carbon, is implied during formal charges, including formal charges. So hydrogen atoms on other atoms such as oxygen, nitrogens must be shown. That's what we did here. We made sure that we showed the hydrogens on nitrogen and oxygen because those are not carbons. Those ones must be shown. Lone pair on electrons are usually not shown unless on special emphasis. Like here you see, I did not show lone pairs, but they are there. You see, these are 6 electrons. 3 bonds means 6 electrons. So I need 2 more to make octet. Here they have 4 electrons to the oxygen. I need 4 more to make an octet. 4 electrons to the shared by the with the oxygen. So I need 4 more to make an octet. You have 2 hydrogens and a single bond here, which means 3 bonds. I could draw the second hydrogen there. So which means 6 electrons, so I have to show 2 electrons as a lone pair to make it octet. So which means here there's a lone pair, there's a lone pair. But we usually don't show them unless where we want to use the lone pair, where we need to use the lone pair to react, or when you're asked to draw the Lewis structure. Then you have to show the lone pairs. Okay. So this is just a continuation of line diagrams, but I want us to look at this structure. I want you to tell me how many hydrogens are here. We have only 1 bond to the carbon. There's a carbon. How many hydrogens on that carbon? Each carbon must have 4 bonds. So there's only 1 bond shown. So 3 hydrogens are there. They're just not drawn. Here I have 4 bonds. So here no hydrogens. No hydrogen missing. And then same applies here. We don't need to imply hydrogens there. The carbon is happy with the 4 bonds. Here there's 2 bonds to this carbon, so 2 hydrogens are missing. 2 hydrogens implied, not missing. 2 hydrogens implied. They're there, they're just not drawn. And then here I have 3 bonds, so 1 hydrogen is present or implied. Here it's 1 bond. 3 bonds are missing on this carbon, so 3 hydrogens are present or implied. if you want to say it so. Here I have a carbon. You remember we said at every end of the line there's a carbon. So the carbon is bonded to 2 bonds as shown. So 2 bonds are not drawn, so which means we have 2 hydrogens. They're just there, they're present, they're just not shown. Again, here's 2 hydrogens, and here I have 3 bonds, so there's 1 hydrogen not shown, but it should be there. So you practice and count how many hydrogens are on this structure. So usually we always want to also to show 3D. So for 3D we show groups away, towards, and on the plane. So for example, if I'm to draw the methane, this is how the methane will look like. Okay, so the ones that I have the straight lines, those ones are on the plane. This one is to the back and this is towards you, just like you would hold your fingers down like this. Okay, so those on the plane will have just lines. Those ones above the plane or towards you will have a solid wedge, which is what we have here, the solid wedge. And then those that are the groups that are to the back, they'll have a dash bond. Okay, so you usually want to keep the angles as needed because here is 109.5. Okay, I've talked about that. So this will be the Lewis structure. Lewis failed because he thought that this should be 90 degrees, but that's not the case. It's not 90 degrees. Okay, this is not 90 degrees because the electrons in the bonds will repel, and they'll repel and maximize their space in space. So the bond happens to be 109.5. Of course, the carbon has 4 electron domains, sp3 hybridized and tetrahedral. Okay, so next time we'll talk about isomers and acids and bases.